This is the second lecture on Text Unit 9 on gases and gas laws. In this lecture, we examine the ideal gas law. We'll see shortly the ideal gas law is an equation of state. In other words, we will use this to describe a gas which is not in process or in situations in which some change is not happening. We've already seen from the combined gas law, P1 V1 over T1 equals P2 V2 over T2. I ask you to remember that another way of expressing this law is that PV over T equals a constant Z, an unchanging number, for any sample of gas. The number actually depends on the sample of gas. It's reasonable to ask, what is the constant Z? The law we will show here is called the ideal gas law. This describes the behavior of gases in most situations except at extremely high pressures or extremely low temperatures. As we can see, the ideal gas law is connected to the combined gas law, which means the same is true of the combined gas law. It describes gases except at extremely high pressures and extremely low temperatures. PV equals T over equals Z for any sample of gas, and it turns out that Z is equal to some constant times the number of moles. So Z depends on the number of moles of gas. And then there is a constant, and this constant is the same for all gases, often called the gas constant, and in this course we will take it as 0.08206 liters times atmospheres over moles times Kelvin. Now attend to the units of the gas constant are liters, atmospheres, moles, kelvins. The expression PV over T equals nR is usually rewritten PV equals nRT. And this is the usual expression of the ideal gas law. The ideal gas law is an equation of state. You can use this law, or is best to use this law, when there is no process to consider. So, for example, here is a state question. At 298.15 K, a gas sample has a volume of 24.466 liters at a pressure of 1 atmosphere. How many moles of gas are in the sample? Right. The gas is not undergoing any change. We just have facts about its pressure, volume, and temperature in a given state or situation. It's asked about the number of moles. We could solve for that by algebraic rearrangement. N is PV over RT. And then we just have to plug in values for each of the four variables. Pressure is an atmosphere, volume 24.466 liters, temperature 298.15 Kelvin. Right. Notice when you analyze the units, atmospheres cancel, liters cancel, kelvins cancels. The answer is 1 mole. It's important to note that in order to use the ideal gas law, we had to have pressure in atmospheres, volumes in liters, and temperatures in absolute units, specifically Kelvin. In other words, these are the units we need, the set of units we need to have to make the ideal gas law work properly. All right. You try this one quickly. Find the volume of 0.000881 moles of gas at 1.09 atmospheres and 302 Kelvin. Stop the presentation and calculate the answer before moving on. We have the appropriate units here, so we just need to algebraically rearrange the ideal gas law, which gives V is nRT over P. We solve for the volume, the thing we want to know about. Put in the moles, the gas constants, the kelvins, the atmospheres. Notice all units will cancel except liters. The answer is 2 liters in this case. Alright, you try this. A 16-gram sample of methane has a volume of 5 liters at 27 Celsius. Calculate the pressure of methane, which is, also natural gas, the stuff we use to heat our houses, or sometimes some of us use this to heat our homes. Calculate the answer before moving on in the presentation. Pressure, algebraically, is nRT over V. Alright, here we have to do some analyzing or work. To find the number of moles, we have to take grams of CH4 and convert to moles. Alright, that's 16 grams multiplied by a conversion factor to give 0.997 moles. Temperature naturally has to be in Kelvin, so we add 273.15 to the given temperature, 27 Celsius, to give 300 Kelvin. Volume we're given is 5 liters. So we insert all the units. Note that all the units cancel, in this case, except atmospheres. And the pressure we obtain is 4.9 atmospheres. Note that if the volume of the gas is relatively small at room temperatures like 27 Celsius, 5 liters is relatively small, you'll have immensely high pressures. Lower pressure, the volume will naturally be, about 5 times larger under similar conditions. Gases take up a lot of space, is one of the take-home lessons from problems like this. A typical question. What's the molar mass of a 3.54 gram of unknown gas at 25 Celsius, 1.56 atmospheres, and 1.74 liters? In other words, the gas is under these conditions, and this is its mass, and you're asked to find the molar mass. You should try this before moving on. Here is the answer. The key to the solution is that we can find the number of moles by calculating PV over RT. Molar mass, symbolized by big M in this problem, is grams per mole. So if we take the mass in grams and divide by number of moles, we'll have the molar mass. But the molar mass is PV over RT. So the molar mass must be the mass times RT over PV. Alright, this is just algebraic rearrangement. The molar mass is then the given mass, 3.54 grams, times the gas constant, times the temperature, 298 Kelvin after we add 273.15, 25 Celsius, divide by PV. Notice we have units of liters and atmospheres, which is what we need to make the problem work. And we're left with 31.9 grams per mole for the molar mass. Now, if we wanted, we could have done this calculation, or you could do this calculation in 2 stages. First, calculate the number of moles from PV over RT. And then just divide the mass by the number of moles. You should obtain the same answer. Here's another one for you to try quickly. At what temperature will 0.0337 moles of gas in a 629 milliliter container have a pressure of half an atmosphere? Calculate an answer before you move on. This is just solving for temperature. T is PV over NR. Volume is given in milliliters. It has to be converted to liters. So we do that first. The volume's 0.629 liters. Units for pressure are okay. Calculate a temperature by plugging in P, V, N, and R. Note that kelvins are the units that survive. They're in the denominator of a fraction and hence come up to the numerator. And the temperature is 114 Kelvin. That's actually negative 159 C, extremely cold. Common question is the density of gases. What is the density of SF4 vapor at 650 torr and 100 C? Alright. You should try this before moving on. Key is similar to the molar mass. This is similar to the molar mass problem. Alright, attend to units. First we have to convert torr to atmospheres for pressure. 650 torr multiplied by a conversion factor. Remember, this is an exact numbers conversion factor. If I assume 3 sigs for the 650 torr, I get an answer of 0.855 atmospheres. Temperature is 373 kelvins to the ones place, which is precise as we have the temperature. Again, I'm assuming the 100 is precise to the ones place. N and V are unknown. We could solve for N over V. That's P over RT. This is moles per liter. Calculate it from P over RT. 0.855 divided by the gas constant. 373 Kelvin. Note that the product of both is in the denominator. Careful with the order of operations. You'll want to calculate this divided by this divided by this. We obtain 0.0279 moles per liter. We can multiply the number of moles per liter, or number of moles in a liter, by the molar mass to obtain a density in grams per liter. Note, since the units of the density were not specified, grams per liter are acceptable. In fact, densities of gases are typically reported in gram per liter units. Well, this is the last example problem, and this concludes the second presentation for Unit 9.